our connection issues. Oh, we're recording. We've resolved our issues, and we're going to have Roberto give his talk. So Roberto Ortiz is a senior lecturer at the Universidad de Sao Paulo. Roberto, could you share your slides?
Can you hear me?
Yes, we can.
Okay, let's go.
So Roberto is going to be talking to us about the new AGB stars showing X-ray emission, binaries, or coronal emission. So if you're ready, Roberto, take it away.
Okay, thanks a lot, Steve. Just a second. Okay. Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. So this is a work that have developed in the last, let's say, 4 or 5 years. So I'm this guy. I work at Universidad de São Paulo. My head works at Instituto de Astrofísica de Andalucía. I'm going to talk about some X-ray emission from AGB stars. So what's the problem with the X-ray emission? Well, let's go back to the 70s, 1979, the time of the IUE satellite. So this satellite detected some far ultraviolet emission from for many AGB stars. I don't know if you are aware that AGB stars, they do have a chromosphere. And we can detect emission line in this chromosphere that tell us the temperature of it. So the Insky-Hash, they proposed that there would be two kinds of UV spectra. What they call the solar type, which means the stars that have a chromosphere, transition corona, and so on, and the non-solar type, showing chromospheres only. That's the case assumed for the AGB stars. The AGB stars do have a chromosphere, but they're not supposed to have a corona. At least this is what we get from the emission lines in their spectrum. 2 years later, Iris and his colleagues, they also proposed the same thing. These are some figures that I took from the papers. You will see the molecular magnitude as a function of the color, which can be read as temperature. The non-solar type stars, which means those that don't have a corona, are the crosses, are located at this region. And the solar type stars are these circles. Well, the place where AGB stars are located is this. If you look, for example, at the molecular magnitude, you figure out that this is the place where AGB stars are. So in fact, AGB stars are in a region where they are not expected to show a corona. The same we can see here in this figure taken by the paper by Iris. The same thing. This is the region where AGB stars are, and the non-solar type spectrum are. But the problem is that X-ray AGB emission has been observed in a few AGB stars. Not many stars, but some. This always started in 1996, the paper by Yorichin. They detected some Rosat X-ray emission from two S-type stars, these two ones. So at that time, they attributed to the accretion of some matter from the red giant into a white dwarf companion. 2 years later, Hunsch and his colleagues, or her colleagues, I don't know, detected Rosat X-ray emission from more stars, one supergiant, one symbiotic, one cataclysmic variable, and many AGB stars. So this increased the number of known AGB stars to about a dozen. Later on, Ramstedt found 13 X-ray stars, AGB stars, using Rosat, XMM, Newton archive observations. And even a few years later, Sahai found some more free X-ray emitters among the AGB stars. They examined they looked for X-ray emission from AGB stars that had some far ultraviolet emission. And actually they found X-ray emission in half of their candidates. So all this sum, the literature consists about 25 AGB stars, more or less, with X-ray emission. So the big question is, where does the emission come from? So there are two obvious possibilities. The first one is that the X-ray emission is the same kind of emission that we find, for example, in the sun, which means it comes from the corona. So corona is a very high temperature layer, the external layer of the sun, so we assume that this corona should be hotter than 1 million Kelvin or maybe a few million Kelvin. Normally, emission from the corona is associated with the dynamo effect, which in turn is accompanied by a strong magnetic field. You might have some local magnetic fields that might be very strong, and the global magnetic field, depending on the structures you're examining in the corona. The fact is that observations have shown that the magnetic field should be less than 100 Gauss at the stellar surface of an AGB star. And this is understood as too weak to confine a high temperature plasma like the corona that we find in solar type stars, for example. And there's more. Some X-ray AGB stars, they show much higher temperatures, for example, about 10 millions or tens of millions of Kelvin. And at this temperature, the plasma cannot be gravitationally confined at the stellar surface. You must remember that the stellar gravity of AGB star is very low. So plasma shouldn't be confined. It should be dispersed. So these are the problems in assuming a corona around an AGB star. We know that they do have chromosphere because we see some emission lines of some species that require temperatures characteristic of the solar chromosphere, but a corona would be much more complicated. So an alternative explanation would be that this emission is due to binarity. So in this case, we should assume, for example, that there is some accretion disk around the companion, normally a white dwarf companion or maybe some late sequence star. But anyway, this also has some problems because, first of all, it's very difficult to find a companion, for example, if in this case is a white dwarf. Remember the case of Myra, the prototype. Myra's companion was observed at the beginning of the 20th century. It was visible for a while and then it disappeared. So nowadays we find only indirect evidence of the companion of Myra, the prototype. So it's not easy indeed to detect the companions of these AGB stars if they do have one. So the purpose of this study is to search for new X-ray AGB stars. So the objectives are these. First of all, to discover new X-ray counterparts of the AGB stars, because so far there are only about 25 objects. If possible, to determine the characteristics of the plasma, it means the temperature, the emission measure, luminosities, etc. And to compile a catalog with all these characteristics of all cases that we know so far. Because we do have this information, maybe you can try to differentiate coronal from disk X-ray emission from AGB stars and answer the question whether the X-ray emission comes from a corona, although we don't know how could it be possible to exist a corona around an AGB star, or from an accretion disk associated with it. So what we did was to search for X-ray counterparts in the 4x Newton 9 version catalog. We just cross-correlated positions. And we use as a sample, as a target sample, 4 samples. First, nearby HB stars, which means stars in the E-particles catalog, with some restrictions of luminosity and temperature, restriction of temperature, temperature smaller than 3500 Kelvin, just to avoid RGB stars. And also a minimum luminosity and a maximum as well, of course, to avoid the RGB stars and supergiants. The second sample was mass-losing HB stars in general. They were taken from a paper by Siebert, 2003. The first sample was S-type HB stars. S-type stars are those that have passed by the third dredge-up episode. So they are HB stars indeed. And the fourth sample was constituted by carbon-rich stars. Of course, they also pass by the third dredge-up. So we tried possible to avoid contaminators. So we more or less have a kind of a pure sample of HB stars. And these are our results. These are the HB stars that we have found associated with X-ray sources. Some of them were previously known as X-ray HB stars. For example, Sahai was published in 2015. Hunch, as I said before. So all these stars that are marked with a comment in the last column were previously known as X-ray HB stars. But those which do not have anything here in the last column, we assume that there are new findings, new discoveries. So we have increased the number of known X-ray HB stars from 25 or less to, let's say, 35, increase substantially the size of the sample of known X-ray HB stars. So I do believe in what I see. So in this slide, I show the X-ray images of the sources compared to the optical position of the stars. And we can see in all these cases, the X-ray positions, they match pretty well the position of the optical counterpart. There's only one case, this one here. This is a carbon star. And the position of the X-ray source coincides more or less with the outskirts of a cluster of galaxies. So this might be a coincidence. We are not sure. But anyway, except by this case, we have found here, let's say 7 or maybe 8 new X-ray HB stars.
Hey, Roberto, 2 minutes.
How much?
2 minutes.
Okay. Okay, these are the results we've got. Here we see let's observe, for example, the X-ray temperature of these our finds. This star, for example, has an X-ray temperature of 80 million Kelvin, which the same applies, for example, for EY Hydra. The temperature is 27 million Kelvin. It's too high to be a corona. So these are the best candidates we have for a binary system and accretion disk emitting X-ray. So we also see that the X-ray temperature that we determined, they match pretty well the previous determination by Sahai and other people. You can compare these numbers. We also determined the luminosity by fitting vector emission to the X-ray spectrum. I'll show you quickly some spectra. the Archer spectrum, we can see the spectrum we're checking at different epochs. We can clearly see a variable, the matter of maybe months, or maybe there are even short-term variability. Why Gemini is a very interesting object? It shows a double peak spectrum. It means this plasma has two X-ray temperatures. So in these panels, I show you the X-ray luminosity compared to the volumetric luminosity. We find a wide range of relative X-ray to volumetric values. And the crosses are symbiotics. So there are some difference in distribution if you compare the symbiotic with the new findings. But we don't know whether this is statistically significant. If you plot, for example, the X-ray luminosity as a function of the temperature, X-ray temperature, in this case, you see that some of them show X-ray temperatures comparable to the corona, solar corona, for example, but others have too high X-ray temperatures to be considered as corona. And these are the candidates to have an accretion disk. In this last slide, I'll show you, you can see a pretty good correlation between the X-ray luminosity and the far ultraviolet emission. And if you make an effort, you can see a straight line here. So the X-ray emission seems to be correlated with the far ultraviolet emission. You can put it like this, like as a function of the far ultraviolet magnitude, absolute magnitude, or as a color. In this case, we measure the amount of far ultraviolet excess. So I'll go quickly through this. We'll go straight to the conclusion because I ran out of time. I just wanted to show you quickly that we have found 17 X-ray counterparts of HGB stars in the XMM Newton DR9 catalog. And among these, 8 objects represent new discoveries. The plasma temperature shows a wide range of values, seen from solar coronal values up to 100 billion Kelvin, which are considered too high to be attributed to a corona, stellar corona. So in this case, these high temperature objects are more likely to be binary systems. And there seems to be a pretty good correlation between the X-ray luminosity and the amount of far ultraviolet excess. So some of these X-ray HGB stars may be actually symbiotic systems, and we must confirm this. We are planning in a very near future, in June of this year and in September, to take spectra from these objects. So we expect to find some emission lines that are characteristic of symbiotics. In this case, we can confirm that they do have an accretion disk. So I'll end up here. If you have any question, please let's do it anywhere because we don't have time anymore. And also this work is going to be published in APJ. So if you want a preprint, please email me at this address. Thank you.
All right, great. Thanks, Roberto. I think we have time for one quick question as the next speaker sets up. So if you could stop sharing and have Emily start sharing her screen. Any questions?
I would like to say it is not a question, it is something like comment. I would like to say that we studied some of the X-ray M giants in the paper of Hyun Chateau, 1998, and we studied them by means the spectropolarimeter Nerval. And for one of them, we found that we have long-term radio velocity variations that presumes a secondary component at a distant orbit. And also it is possible to be a dwarf star, and that could explain the X-ray emission of this star. In addition, the M giant is magnetically active, but it is at the same place that you say that it is not likely to have corona. And it is rather possible the X-ray to be the reason for the X-ray to be the dwarf. So you have to consider not only the symbiotic stars, but you have to consider as a possibility white binary with dwarf component, as we were surprised by this long-term study. Thank you.
Okay, thank you.
Great, thanks. All right, I now have the distinct privilege to introduce our next invited talk by Emily Levesque. She is a professor at the University of Washington. She's won a number of awards, including the Annie Jump Candidate Award and more recently the Newton Lacey Pierce Prize. She wrote a book, which I can say was an absolute delight. But today we're gonna be talking about Betelgeuse, which is pretty cool. Cosmic questions for our naked eye neighbor. So Emily, go ahead and take it away.
Excellent, thanks for the intro. And it looks like everybody can see and hear me just fine.
Yep.
All right, excellent. So I know that a lot of our Betelgeuse talks are happening tomorrow when I'm unfortunately going to be very asleep, but I figured that this talk could serve as a sort of general introduction to what we'll be hearing about related to Betelgeuse, some explanations for what it did a couple of years ago, and how that ties into many of the topics that have been covered in the conference. So just to start off, as a reminder, Betelgeuse caught everybody's eye about a year and a half ago in late 2019, early 2020, when it did this, essentially. The star dimmed from, I can't seem to advance my slides, there we go. Let's back that up again. The star dimmed substantially to the point where it was easily noticeable with the naked eye. It went from the brightest star in Orion to, I think at one point it was the third brightest. It caught a lot of amateur observer attention. It wound up making headlines because everyone was convinced this meant it was about to explode. But it caught the curiosity of the cool star community, mainly because we wanted to explain why this unprecedented dimming was happening. The best picture by far of what Betelgeuse actually did was this pair of images from Miguel Montargis, who we're going to be hearing from tomorrow. And you can see this amazing comparison between what Betelgeuse looked like in January of 2019 versus December of 2019. And you can see that it has appeared to get dramatically dimmer. The dimming seems very concentrated in the southern hemisphere. And you can see just by watching this how this would wind up manifesting observationally. And this continued to an even greater extreme once we got to February of 2020 when it hit its dimmest point. So the question that everyone kept posing was, what is Betelgeuse doing? What can explain this very dramatic dimming? And there were three different ideas that had been floated. So yes, again, we're going to have a talk coming on Friday. One was that cold patch that you could see in that picture had to do with a cold spot appearing on Betelgeuse's surface due to convection. We know that red supergiants have enormous convective cells, and it was possible that that dimming was explaining what we were seeing. There was also the possibility that this wasn't that strange, that this was simple part of the normal variability that we see in a number of red supergiants. Betelgeuse is a known variable, and when you look at its light curve, you see the great amount of variation that's already going on. So maybe this was just nothing particularly out of the ordinary. And then the third idea was that this could be attributable to mass loss and dust production. So a cloud of dust that was temporarily obscuring our view and making Betelgeuse appear dimmer than it was. All three pictures that I've put here are artist renditions. I prefer my own versions of these artist renditions stolen from XKCD. So we will go through some of the physics for red supergiants in general and Betelgeuse in particular regarding the cold spot that might have appeared and the physics of convection in these stars' atmospheres. We will talk about other ways that we might see red supergiants vary, behavior related to multiplicity or rotation. And we will look at some of the mass loss and dust production that could be going on in these stars due to winds, due to dust condensation, and what this winds up implying for Betelgeuse or red supergiants as a whole. So we'll start by looking at convection and the idea of a cold spot on Betelgeuse's atmosphere. So as a reminder, when you look at the optical spectra of red supergiants, we have fantastic thermometers that can be used to measure these stars' effective temperatures. This is an animation of the Marks stellar atmosphere models for red supergiants, and you'll watch the animation cool the stars from 4,000 Kelvin down to 3,400 Kelvin, and this corresponds to a spectral type shift from about K1 to about M5. And as you do this, you watch the big booming titanium oxide bands appear and then get rapidly broader and broader and deeper. So the depths of these titanium oxide bands are an excellent way of measuring the surface temperatures of red supergiants, or at least the surface as we define it when we're talking about optical light. So with this in mind, taking a spectrum of Betelgeuse and comparing spectra of Betelgeuse before and then during its dimming seems like an excellent way to get at explaining this star's behavior. We also know that red supergiants have enormous convective zones. So this is a kind of classic Kippenhahn diagram of a 15 solar mass star as it goes through its evolution. And you can see that by the time we've moved into the red supergiant stage, there's this big convective envelope. It's illustrated by the little parentheses, but you can see the extent to which this star is almost fully convective and the sheer scale on which convection would be going on. This is wonderfully illustrated by these simulations of red supergiant surfaces, where you can see a small handful of convective cells with scales on the order of the radius of the star just boiling away. And from looking at this, you can easily imagine how this would contribute to variability in general, and potentially to even extreme variability if a particularly cold patch of the star came to temporarily dominate the surface. So this was the idea that we decided to explore when we were trying to explain Betelgeuse's dimming. We know from beautiful observations of Betelgeuse that it does have this kind of patchy surface, and we see evidence of these convective cells. So was it possible that this change from January to December of 2019 was just the presence of a cold patch in Betelgeuse's southern hemisphere due to the natural convective behavior of the star? Phil Massey and I got curious about this in around February of 2020, right as Betelgeuse was approaching what would be its dimmest point. We had an old spectrum of Betelgeuse taken way back in 2004, and we had assigned it a temperature of about 3,650 Kelvin based on the depths of those titanium oxide bands and a best fit to those Marks stellar atmosphere models that I showed before. So knowing that we had an archival spectrum of Betelgeuse from when it was normal, we decided to try and go after a new flex-calibrated spectrum of Betelgeuse during its dimming to compare the two. So we did this using the Lowell Discovery Telescope, which is a 4.3 meter telescope in Arizona. And as an amusing side note, a 4.3 meter telescope is enormous to be taking a spectrum of something called Betelgeuse, of something as bright as Betelgeuse. We had about a 7 magnitude neutral density filter that we could use for the observations themselves. A funny catch was that there was no neutral density filter for the acquisition camera. So Phil wound up acquiring Betelgeuse using the edge of the dome to lock onto the star. And then once it was acquired, we were able to put Betelgeuse into full view and take a spectrum with a big neutral density filter. So this is a plea for remembering that little telescopes with great spectrographs are a really valuable tool for studying a lot of the stars that we've been talking about during this conference, and stars like Betelgeuse in particular. So when we looked at our new spectrum, the comparison was really interesting. You could clearly see from the flux of the spectrum that Betelgeuse had dimmed. The dimming is especially pronounced over at redder wavelengths. And the titanium oxide bands, by contrast, are not that much stronger. The star was not that much colder. We wound up assigning this new spectrum a temperature of 3,600 Kelvin, so a little bit colder, but a difference of 50 Kelvin is really quite minor. You can see a better comparison of it in this figure where we flat out overlaid the 2004 and 2020 spectra, and you can see the very clear and consistent agreement in depth between the two lines. So the spectrum of Betelgeuse had cooled only very slightly in the midst of this great dimming. So what we wound up concluding from this was that dimming on its own, or that cooling on its own, was not enough to explain the great dimming of Betelgeuse. A net drop of 50 Kelvin in the collective surface temperature, which we would then expect to cause a slight drop in, black body emission and a slight drop in brightness, doesn't explain the very severe drop that we saw in the star's light curve. Now, I know there are more papers on this that are still coming out, and there's more work that we're going to hear about in this conference. There was some great work done by Harper et al. Looking at what would happen if you took Betelgeuse and sort of made a composite spectrum, combining a region of the star that was that original temperature of 3650 Kelvin and a region that was much cooler of about 3300 Kelvin. This is an excellent way to potentially explain why the star could look dimmer, but the aggregate temperature is still 3600. So regardless of whether this is a cold patch or something else, the dimming needs a lot more of a temperature drop in order to be explained by temperature alone. There is going to be more on this during the conference. There's a poster in Gathertown and another talk coming on Friday that I encourage everybody to check out, because I know we'll be talking a lot more about Betelgeuse. But explaining the dimming with temperature alone suggests we'd need a much bigger decrease, and it suggests that maybe the cold spot from convection alone isn't an explanation for what Betelgeuse did. So our next option is to look at normal red supergiant variability and consider whether we're just seeing a conflation of different phenomena or something that should be fairly typical for red supergiants. If you look at Betelgeuse's light curve, you can see the nice regular variations in the light curve. These have been associated with a pulsation period estimated to last about 430 days. And it's interesting to note that based on Betelgeuse's dominant period, its next minimum should have been around the second half of February 2020. And that was exactly when the minimum of this great dimming happened to occur. So the timing really was compelling. But to address this, we want to think about all the different ways that we could see regular or semi-regular variations in red supergiant brightness. And there's a lot of them. We've heard about some of them so far in the conference. One in particular that our group has been curious about as part of studying red supergiants as a whole is the contribution of binary companions to these stars' light curves. Binary evolution should dramatically impact how red supergiants lose mass, how they evolve, and how they die. But we knew shockingly little about binary red supergiants just a few years ago. And this is interesting because we really want to quantify the red supergiant binary population and understand the evolution of these systems, because this becomes key for then understanding massive star behavior and how these stars die. So the question then comes up, well, how can we identify binary red supergiants? How can we start building up a sample that we can study? We can't do it from their light curves, and this is unsurprising just based on that animation that we saw earlier. This is made extraordinarily difficult by the large number of different phenomena that affect red supergiant brightness. So we tried to look at a different means of identifying red supergiant binary companions. So this is work that Catherine Nugent has been doing at the University of Washington, or Dr. Catherine Nugent, because she just defended a couple months ago. And her thesis was focused on how to find red supergiant binaries. The first interesting result that we came across was that almost all red supergiants will have B star companions. And this is simply a function of star formation and timescales. If two members of a binary are born together, a more massive star that becomes a red supergiant will have entered and then completed its red supergiant evolution before a low mass star will have even made it to the main sequence and finished its pre-main sequence evolution. The exception of this is stars that are relatively close to it in mass, which will land on the main sequence as B stars. So with the exception of the rare systems where the red supergiant is the secondary, these stars should have B-type companions. Catherine was then able to take that fact and look at what composite spectra of red supergiants and B stars would look like. And what she identified was that, one, you can see a spectroscopic signature of the B star over in the blue side of a red supergiant spectrum. You see these telltale upper Balmer lines in absorption. But you can also identify these stars photometrically because of the contribution that that B star is making to the blue side of the SED. Catherine wound up making a bunch of composite red supergiant and B star spectra. You can see some examples of them here, going from pretty cold red supergiants paired with B supergiants or dwarfs to relatively warm red supergiants in the same scenario. And you can see the very notable effect that the presence of the B star has on the SED. If we then take all of these models and drop them into a color plot, you can see a big triangular region that should be dominated by red supergiant B star binaries. And it's very distinct from B stars alone or red supergiants alone. Catherine then turned this from a theoretical prediction into an observational test and was able to use these color plots to identify red supergiant B star binaries. The number of known red supergiant B star binaries has gone up by an immense amount, and you can see in these example spectra just how noticeable these are. These go from stars where, looking at the spectrum, it's immediately obvious that there's a companion. You can see the big upturn in the blue and the absorption lines, to stars where it would be very subtle. You would not ever recognize that that star on the right is a red supergiant with a blue binary companion unless you really looked in detail at the very blue end of the spectrum with a very good signal to noise in order to identify those absorption lines. So in the end, what Catherine was able to determine is that the red supergiant binary fraction is around 15 to 30% of red supergiants. 15 to 30% of these stars will have B star companions, and very interestingly, this binary fraction also appears to increase with metallicity. So the plot shown on the left right now is showing the red supergiant to OB star binary fraction as a function of, on the x-axis, distance from the center of M33. So we're close to the center on the left and far from the center on the right. And M33 has a very well-known metallicity gradient. So it's a very compelling suggestion that we are going to see a metallicity dependence on these stars' binary fraction. We do not yet have a measure of how many of these binaries are interacting and what that does to the star's overall evolution, and we don't see clear signs of these binaries in the light curves, but it's a really interesting result in terms of understanding red supergiant evolution. And I know we'll also be hearing more about this on Friday as part of Lee Patrick's talk on the multiplicity of red supergiants. So we know that multiplicity is going to be an important period in red supergiants, and this becomes especially evident when we look at their evolution. Massive binaries will most likely be too wide for interactions to impact stellar evolution until one member becomes a red supergiant. Once it becomes a red supergiant, it undergoes Roche-Loeb overflow, it kicks off mass transfer, it circularizes the orbit, and we start to see the evolutionary effects of this mass transfer on the red supergiant and the red supergiant population. So this is very evident if we look at evolutionary tracks for massive binaries and watch how they change as we go from single stars to interacting binaries. So this is from work that Trevor Doran-Wallenstein did. He's also a graduate student at UW, and we'll be taking a close look at what he found very soon. So this is comparing single star evolution models from the BPAS group in New Zealand to the evolution of models that are undergoing fairly typical binary interactions. And you can immediately see what this does to the red supergiant population. Higher mass red supergiants become rarer, and the evolutionary state that these stars are at, depending on their position on the HR diagram, changes as we see the effects on the star's outer layers of this binary interaction. So this was part of Trevor's thesis research. And what Trevor was able to find by modeling entire populations of both both single and binary massive stars was that this would have a major impact on the populations that we saw of red supergiants or other evolved type stars. You can see in this plot that we're plotting time evolved for a stellar population on the x-axis and the number of red supergiants on the left and Wolf-Rayet A stars on the right on the y-axis. And you can compare the populations produced with a binary fraction of 0 and a population where every star is in a binary. You can see how much binary evolution decreases the expected population of red supergiants, and on the flip side, how much it increases the expected population of Wolf-Rayet A stars. So it's a very clear illustration of just how much binary evolution will affect red supergiants. One interesting complication, though, is that binary effects can be conflated with other effects like rotation. If you look at the number of red supergiants and the number of Wolf-Rayet A stars produced in a population of entirely binary stars or a population of entirely rotating stars, they're surprisingly similar. So we know that things like binary evolution and rotation will affect red supergiant evolution. We anticipate that it will affect things like their light curves, but it's very hard to disentangle, and picking these effects out of red supergiants' more broad variations is very hard to do. So this is some of the work that Trevor's done for his thesis. If you want to hear about more, I would suggest going back and watching his talk from Tuesday. He's also done some amazing work looking at pulsations and the behavior of massive stars with TESS, including some really interesting work on pulsating yellow supergiants that we think might represent a post-red supergiant population. So be sure to check that out if you'd like to see more about Trevor's work. So,
hey, Emily, 2-minute warning.
Yep. Excellent. So, in aggregate, we can see an example of what red supergiant binary evolution could do for these stars as a whole. In the case of Betelgeuse, we don't think that that is what is going on with its great dimming. We don't think that that is what is explaining its light curve. What we've seen is that Betelgeuse is possibly the product of a past merger. It's rotating pretty rapidly for a red supergiant. But if we look at its overall light curve, this is not most likely what is explaining the great dimming. So we've kicked out normal red supergiant variability. And now we'll get on to the final potential explanation and what we think is the key for explaining Betelgeuse's great dimming. So we know that red supergiants shed an enormous amount of mass from their outer layers during their lifetimes. We know, as you can see from the HR diagram on the right, that this can dramatically impact their evolution, and we'll be hearing more about this in the very next talk after mine by Roberta Humphreys, along with more discussions on Friday. So if we look at the effect this has on a red supergiant spectrum, we know that red supergiant dust appears to be larger grained and grayer than classic interstellar medium dust. And what this means is that if we compare the data from a red supergiant in black to, say, a model without any dust in red, you see a blue or near UV excess in a red supergiant that is being reddened with this large grain gray dust. It is not what you would anticipate if you just in aggregate started to dim a star using classic ISM dust. We think that that is what we are seeing happening in our spectra of Betelgeuse. We can see that the star has gotten dimmer, and we think that this dimming can be explained by dust because the dimming is very evident in the red, but you see a relative excess in the dimmed spectrum of Betelgeuse in the blue. So our expectation is that going from January 2019 to December of 2019, we are seeing the presence of a mass loss event condensing into dust and blocking our view to Betelgeuse that is present primarily in that southern hemisphere. So if we go back and look at the collective effects that we expect to see on Betelgeuse, the combined research that's been done suggests that we're seeing several different phenomena. We know that the dimming was clearest in the southern hemisphere. We see some evidence that Betelgeuse was cooler or perhaps smaller during this time, but that alone is not enough to explain the star's dimming. We do instead see evidence of large grain gray dust blocking light from Betelgeuse, and this has been borne out in other observations that have happened since ours, and this seems to be associated with an earlier mass loss event. And in turn, we believe that that mass loss event could have potentially been prompted by normal pulsations and convection. So the takeaway from this is that all of these phenomena likely combined to give us the burst of mass loss and subsequent dust and subsequent dimming that we saw from Betelgeuse. The key takeaway that I like to think of looking at Betelgeuse as compared to red supergiants as a whole is that none of this should be unique to Betelgeuse. We should see similar behavior in other red supergiants. And I should point out that I made this ending slide before reading the abstract for our next talk by Roberta Humphreys, but more discussion of this is going to be coming very soon, because knowing that Betelgeuse is just one example gives us a really interesting lens for looking at other extreme red supergiants and how they shed mass and how they evolve. So on that note, I'll leave this final slide up, and I'm happy to take any questions. Thanks.
Fantastic. Thanks, Emily. We have time for a couple questions.
Craig has his
hand. Yeah, with some hands raised. Yeah, go ahead, Craig.
Yeah, Emily, thanks. That was a great talk. I tried to absorb all of it. I'm compelled to ask about the merger. And so you mentioned that very briefly. What do you think the possibility is that Betelgeuse has had a merger? And what should we look for to try to confirm that?
Well, so this is actually something that Catherine Nugent is going to be exploring as part of her postdoc research, because it was the kind of final piece of her thesis observations. Betelgeuse and other red supergiants may well have undergone mergers. Because they're at their largest point, it's the most likely point in a binary's evolution for common envelope evolution and a merger to happen. And I think this argument of the higher rotation rate is a really compelling one. So what we're hoping to do with the data that we already have is to look at the rotation rates of a large number of red supergiants, see how they're distributed, see what that implies about mergers, and then possibly think of other tests for detecting the presence of basically a star that's been eaten by the red supergiant. Now, whether that's going to be abundance related or have something else to do with the appearance of the star, I think probably requires more modeling and more work, but we would love to be able to distinguish the post-merger and not post-merger red supergiants, because right now they look deceptively single, but knowing how many of them have merged makes a huge difference when we talk about how these evolve as a population.
Yep, great. Now I'll look forward to all that work. It's going to be exciting. Thanks.
Yeah.
Great. We have another question from Eric O'Melian, who's asking, how large are the dust grains?
Excellent. So we don't have, as I recall, we don't have a measure of the dust grain sizes around Betelgeuse in particular, but there's been some great work with coronagraphic imaging or other observations of the surroundings of red supergiants. If I'm remembering correctly, the dust grains are like 0.3 to 0.5 microns. They get pretty big. We are hoping actually to get some data on Betelgeuse that will allow us to actually measure the size of the dust grain by getting, color data on the dust around Betelgeuse itself in particular. But the idea that dust grains around red supergiants are large is pretty well backed up by other observations of really dusty stars. I'm sure we'll be hearing more about that later in this conference. And now the question is just to get a number on Betelgeuse in particular. I do know that there were observations planned of the dust around Betelgeuse during the time of its dimming. I know that there was some great SOFIA data that was taken and that more was scheduled. We were looking at trying to get ALMA data, and it was right when observatories were closing in March and April of 2020. So we missed a chance to look at this dust, but looking at the dust in general should still give us a pretty good answer.
All right, great. Well, I do think we have to move on, but there'll be plenty of time for discussion later on. So if you can stop sharing your screen. Our next speaker is Roberta Humphreys, as was said, a professor at the University of Minnesota, and she's gonna be talking about the recent mass law history of the red hypergiant VY Canis majoris. So Roberta, if you'd like to share your slides.
Can you see that? Hello?
We can hear you, but we can't see your slides yet.
Oh, darn. Okay. Can you see it now? Oh,
Bingo.
Yep,
We got it.
Yep, we can see it.
okay. Here we go. All right. Well, this is pretty much going to be a lot like the talk I gave a few weeks ago at the Cool Star Conference. But at the end, I want to do a little discussion more of the evolutionary state of VY Canis majoris and its possible fate, what's going to happen to it. So just to begin with, I should mention that this is basically a summary of two recently published papers based primarily on Hubble observations of the ejecta of VY Canis majoris. Papers are listed here, as well as my collaborators on those papers. Most of the observations, as I said, come from the Hubble Space Telescope. For those of you not familiar with this amazing red hypergiant star, I've listed here on this slide a few of its basic parameters. Very simply, it's one of the most luminous known red supergiants and one of the largest stars we know of. It's also a very strong infrared source and a powerful source of laser emission. In the infrared at 10 and 20 microns, it's one of the most highest flux stars at those wavelengths. There you see two of the famous Hubble images of VY Canis majoris with its very well complex circumstellar ejecta, I think as best we can describe it, very asymmetric with prominent arcs and several small clumps of knots quite close to the star here. Just a little bit of background so understand how we get some of the numbers we obtain is that over the several years, we attained first and second epic images with the Hubble in '99 and 2005, also with long slit spectra from the Keck telescope in 2002. This image shows the position of Keck slits across the ejecta. Here I show two images, 2D, these are two-dimensional spectra, 2D spectra of the potassium-1 doublet emission line in VY Canis Majoris. Interestingly, the strongest emission line in this star is potassium-1. I show these two 2D spectra for a reason, and that is to illustrate that the potassium-1 emission is a good tracer of the gas. This particular upper figure shows one of the slits that goes right across the star. And when you look here, you see here's the basic systemic emission on potassium-1 from the background nebulosity. And this feature right here is the northwest arc going right across through here. So you clearly see it kinematically separate from the background emission, from the background emission nebulosity. Slit 5 is even more interesting, going right across two of the prominent arcs, arcs 1 and arc 2. And of course, here's the emission from the star. But notice this interesting emission feature stretching over 2 arc seconds on the sky. It begins right at the edge of arc 2, stretching all the way to the leading edge of arc 1. So this is clearly an outflow of gas and visible in potassium-1 emission. Here you see 2 more emission knots. They are identified with the position of what we call arc 2, one at the systemic velocity, and the other one here coming from emitting gas associated with this second arc. Well, the information we can obtain then with 2 epochs of images is, first of all, we measure the proper motions from which we determine the transverse velocity. From the potassium-1 emission, we have the Doppler velocity. Combining all of that information together, we can determine the total velocity of the star, total velocity of the ejecta relative to the star, the direction the ejecta is moving, its orientation with respect to the plane of the sky, and the time of the actual ejection, the age of the ejection. And looking here at this image, I've identified some of the more prominent features, the northwest arc, arcs 1 and 2, several clumps of knots close to the star. One of the points I want to make is with this information, direction of motion, orientation, for instance, the northwest arc is actually projected behind the plane of the sky. Arcs 1 and 2, however, are in front of the plane of the sky, and arc 1 is actually in front of arc 2. So we can determine not only the direction they're moving, northwest arc, not surprisingly, just as it looks like it's moving in this direction, but it's behind the plane of the sky. These two are in front and sort of basically moving towards us. So just wanted to show this to give you your orientation with respect to the circumstellar ejecta. What are we looking at here? Well, unfortunately, with the ground-based observations we obtained earlier with Keck, we were not able to actually resolve the individual knots that are very close to the star. So we obtained narrow slit observations with the STIS on the Hubble in 2018. And the biggest surprise was when we looked at the spectra taken directly on the star, and spectra of the individual small resolved knots close to us, we had a surprise. For decades, I think astronomers had concluded that these very strong potassium-1 emission lines, which dominated spectra, were coming from the star itself, specifically due to resonance scattering in the complex circumstellar ejecta immediately around the star. So it was our surprise when here on the panel you see on the left, looking at the spectrum of the star itself, Well, potassium-1 emission is there, but it's not strong potassium-1 emission. And again, here's the spectrum in the red showing the famous calcium-2 triplet. When we looked at the spectrum of the knots, one of the knots quite close to it, we see this very strong potassium-1 emission, also things like rubidium-1 in emission as well. And when we look at the red spectrum showing the calcium-2 absorption triplet, there they are. But in addition, strong molecular emission. In this case, this very peculiar looking emission feature is due to titanium oxide. So we were left sort of with an astrophysical problem. What was the origin of the excitation then of the potassium-1 in the knots and the molecular emission? Well, thinking about that problem for some time, we came to the conclusion that these knots over here on the west side of the star must have a clear line of sight to the star. So that kind of punches a hole, literally a hole, in this model then that VY Canis Majoris was surrounded by an obscuring circumstellar envelope. If there is such an envelope, it's got holes in it or gaps. Well, in addition, of course, we were able, combining our information on the proper motions of the knots with the radial velocities, we were able to determine their ages and the times of ejection. In the case of these knots very close to the star on the east and west, most appear to have been ejected in the early 20th century. In addition to those observations, we also obtained long slit spectra with STIS of several of the knots actually to the south and southwest of the star. I've only summarized the results here for a few of them. There were other measurements, but these show the ejection ages and times for those that correspond to ejection during the 19th century. I want to, however, emphasize that not all of the knots, emission knots surrounding VY Canis Majoris are visible, that is, in the optical. Actually, there are several obscured clumps of knots that have been resolved in images with ALMA, and you can see them here. In this picture on the left, this is the 1 micron Hubble image. There, as you can see, the northwest tail. The star is located here, and you see the ALMA detection of several small knots just to the north and east of the star, very close to the star, just like those little optical knots that we resolve with Hubble. And here you see a better image resolving the separate clumps that are seen with ALMA. Remember, we don't see these in the optical at all. So in order to estimate the age of these clumps, I use one of them here, the most prominent one, clump C. We just assumed that it had the same total outflow velocity relative to the star as the other knots that were very close to it. Actually, because clump C turned to be about the same distance from the star as those other optical knots. In addition, kind of unexpectedly again, we found a potassium-1 emission knot very close to the star, revealed only in the spectra, only about 50 milliarc seconds from the star. And again, assuming an average velocity for that knot as well, it had a fairly recent ejection sometime around 1985 to 1990. So the next step was then to compare the ejection times or ages of these knots with the historic light curve for VY Canis Majoris. And I want to take a few minutes to explain the light curves. This is quite interesting and a very important result. Just to kind of summarize it very quickly, we find that several of the knots ejected during the 19th and 20th centuries agree with deep minima in the light curve of VY Canis Majoris. This first panel here, the upper one, is the light curve from the 19th century. Yes, indeed, I said that, 19th century, going all the way back to 1800, which is very interesting. The star was marginally visible to the naked eye in 1800. Today, it's now about 2 magnitudes fainter than that. Well, unfortunately, the historic data is somewhat incomplete. As you see, there are some big gaps. Nevertheless, there were at least 3 minima in the time around 1870 to 1880, in which the star declined by about 1.5 magnitudes. After each minima, it returned basically to its former brightness, except sometime between about 1880 and maybe 1890, it did not return to its former brightness, and that's when it declined by about 2 magnitudes. The middle panel actually shows these, by the way, I'm going to emphasize these are visual magnitude by eye. The second panel uses the Harvard photographic survey, and this is the light curve from the photographic survey by the Harvard College Observatory from about 1890 up to approximately in the late 1960s. The second panel here in the 20th century is particularly interesting because you see several well-defined deep minima, 1.5 to 2 magnitudes. The duration is also important, about 3 years. Some of the shortest ones around 2 years, longest ones around 4 years. And again, as you can see, most of the time the star returns to its former brightness after the deep minima. And several of these clumps that we observed, the knots we observed, agree with this very active period lasting about 20 years in the early part of the 20th century. The third panel is the more recent data from the AAVSO. Again, this is visual photometry, again, measured visually. And you see at least 3 minima occurred sometime around 1985 to 1995, lasting about 10 years. And that innermost knot that we found only in the spectrum agrees with ejection at that time. I'm going to suggest that these deep minima are due to the formation of dust. First of all, you see the star returning to its former brightness after the deep minima. But bear in mind what we're looking at here. As I tried to emphasize when we looked at some of the other large-scale ejecta, the giant arcs, is that they are ejected in different directions, different orientations with respect to the plane of the sky. They are coming from different regions on the star. So think about a gaseous outflow, an ejection occurring. It moves outwards from the star. Initially, it's going to be in our line of sight. As it moves away from the star, gets to a distance where dust forms, it's going to begin to obscure the light of the star. But over time, over a period of a year or two, a few years, like in most of these cases, maybe 3 or 4 years, it slowly moves out of our line of sight because it's moving in a different direction, has different orientations with respect to the plane of the sky. So that's why over a period of time, which may be only a few years, the star slowly recovers and comes back to its former brightness. So that's what I emphasize here, that these massive outflows are in different directions, that they form dust, which temporarily obscures the star, except perhaps in the late 19th century, 1880, 1890. I'm going to hypothesize that the star had a major outburst, a major outflow that was nearly in our line of sight and has remained nearly in our line of sight. And that is why the star dimmed by about 2 magnitudes. Now, this is important with respect to what I said earlier about these potassium-1 lines, the molecular emission coming from knots, not from the star, but from knots off to the side of the star. That required a clear line of sight to the star. So instead of a general obscuring cloud, a circumstellar cloud around the entire sky, that we actually have simply a knot, a very dusty knot of ejection obscuring our line of sight today to the star. That actually is supported somewhat by, they're sometimes referred to as the southwest clump seen here. These are infrared bright knots, all close together. And they also require a nearly clear line of sight to the star to explain their infrared emission. One of the pieces of information we get from the infrared observations and from the ALMA observations is estimates of the total mass of the knot or clump of knots. And those numbers indicate something like on the order of 100th of a solar mass associated with the infrared emission coming from the southwest clump. And for the ALMA clump C, the very large prominent one, it's a 5 × 10⁻²⁰ solar masses. So the masses of these clumps is quite significant, sort of like 2 or 3 times the mass of Neptune.
Hey, Roberta, your time is up. So could you wrap up?
Okay, all right.
Thanks.
One of the points I wanted to make was that you can kind of estimate the total mass loss using those minima in the 20th century. You get a fairly high total mass of 7/100ths of a solar mass, giving you a mass loss rate of the order a few times 10⁻³ solar masses per year. And actually, when you compare that over a period of time, it turns out that you can explain VY Canis Majoris's high mass loss rate that we observe today is due entirely to these high mass loss episodes, these individual ejections. So origin of the mass loss, well, I'll just simply conclude then with saying I think it's due to large scale surface activity, but on a much grander scale than, say, we observe in Betelgeuse. And whether or not they're magnetic fields, and the answer is yes. It's somewhat circumstellar, but it comes from the Maser observations. Okay.
Great, thanks. We have time for some quick questions. We got a couple hands up. Yeah, want to go ahead, Ambish?
Yes, hello, Dr. Humphreys. I'm one of the students of Dr. Juris. I have two short questions. Because of these very complicated asymmetric outflows, can we even classify the envelope of these supergiant stars into inner wind and outer wind and dust condensation region like we do for AGB stars?
I'm sorry, I didn't understand. What was your inner and outer? What were you talking? Inner and outer.
Inner part of the envelope, and the outer part of the envelope, the dust condensation region. We have classified the envelope of AGB stars so well. Can we even do that with stars
we don't really. Okay, that's like at this stage with a star like VY Canis Majoris, we don't really see an inner or outer envelope. These knots and arcs that you see here, perhaps I should have emphasized, these are hundreds of AU, thousands of AU away from the star.
Okay, and my next question is the reason these knots are formed in this outflow that are so massive have anything to do with the nucleosynthetic process?
You mean in the interior?
In the interior, in the core of the stars.
Well, that's an interesting question. I didn't have time in one of the last slides I wanted to show. In fact, take advantage of the question. Okay, one of the interesting things about VY Canis Majoris is its complex chemistry. Over 25 molecules, including some carbon-based molecules, have been identified in its ejecta. And some of these molecules, interestingly, seem to be associated with specific outflows. This is from the work by Lucy Zierich. Specific outflows, a blue shifted outflow, which would correspond to arcs 1 and 2, and a red shifted outflow corresponding to the Great Northwest Arc. So that's a very interesting chemistry, suggesting, and I'm going to suggest, in fact, was that VY Canis Majoris is a highly evolved red supergiant. It may be near the end of time, or it might even be an example of a second generation red supergiant, sort of corresponding to what we see with AGB stars, a second generation red supergiant in a very short-lived high mass losing state. Does that answer your question? We don't know the answer to your question, but there's a lot of intriguing data information out there that is suggestive.
Yes, I am one of the students of Dr. Juice, and we are trying to study another supergiant stars, and we were having the same kind of problems modeling the envelope where you have very complicated outflows. Thank you so much.
Okay.
All right, I think we do have to move on. So thank you, Roberta. Our next speaker is Greg Sloan, someone else at the Space Telescope Science Institute. And I'm going to share his slides, but he's going to be talking about the final stages in the lives of carbon stars. So I'll go ahead and share my screen.
Let's do a sound check. Can you hear me, Steve?
We can hear you, Greg.
Good.
Whoops.
Sound check is good. You can start in the middle if you want. That'll speed us up because we're a little behind. Okay, so I first want to thank the organizers for giving me a chance to speak. And I'm sort of speaking on behalf of both me and Kathleen Kramer, who's at Boston College, and I am at the Space Telescope Science Institute, like Steve said. I'm also adjunct at UNC Chapel Hill. So I want to start with a pretty picture, not my own. This is basically from interferometry showing the disk of our sculptor. And you can see what is believed to be the effect of dust. And so it's kind of a patchy looking photosphere, but that's actually the dust. All right, let's go on. Let's start rolling. Number 2. So we have to go back to the Spitzer Space Telescope, which some people may remember, and the SAGE, which was surveying the agents of galactic evolution. That was Margaret Meixner's survey of the Large Magellanic Cloud. And this is actually, of course, that was followed up by Carl Gordon's SAGE SMC. So an all galaxy survey with IRAC and MIPS, so multiple infrared channels. And if you marry that with 2MASS, you can produce these color magnitude diagrams, which is what Bob Blum did in 2006. And he used this to identify various regions in the AGB. So he identified the oxygen-rich AGB in blue, the carbon-rich AGB in red, and then the extreme AGB in, I guess that's yellow here, because it wasn't clear if those were just oxygen-rich stars or just, well, we knew there was mostly carbon-rich, but there could be some oxygen-rich pollutants in there. So better to be a little careful. Let's go on to slide 3. But I wanted to look at this in a different, from a different angle. So I used the Ogle 3 survey and basically followed their lead, took all their carbon stars, and this is the SMC here, but the LMC and SMC are very similar, except there's fewer data points in the SMC, so you can actually see what's going on. But the fundamental pulsation sequence here, which is populated with the orange and the red symbols, those are Myra's and semi-regular variables, both. And then the overtone sequence, which is the first overtone to the left in light green, those are all semi-regular variables. And the distinction between the two is simply 0.8 magnitudes, peak-to-peak amplitude in the I band. That was the Ogle 3 definition. And it's interesting to note that most of the stars on the fundamental mode are not pulsating that strongly. Those are the SRVs. Let's do slide 4. So if you take that information and use it to color code and then map back into the color magnitude diagram that we were looking at before, so the vertical dotted line, that's the boundary defined by Blum et al. J minus 3.6 is equal to 3.1. That's the boundary between the extreme AGB and the carbon AGB. And you can see here pretty clearly that for the carbon stars, the difference between the two is simply that the redder sources are Myra variables. So they're on the fundamental mode, they're pulsating in the fundamental mode, and they're pulsating strongly. And everything else, whichever mode it's in, it's a weak pulsator, and they're all over here in what was previously just called the CAGB. Slide 5. So yes, Spitzer. This is a picture I took pre-launch before I realized that we weren't supposed to take pictures. And I just wanted to point out that the IRS on Spitzer took a sample of 184 spectra, most of them the LMC, of carbon stars. So we basically kind of combined all the data from a lot of different programs and published this. It's been 5 years now. And you can see that reference if you want to see all the people that contributed, because a lot of people put a lot of time and effort into this. Slide 6. So with that many spectra to deal with, we have sort of a brute force method of processing the spectra fairly quickly. This is called the Manchester method. And you can see the idea is that for each spectrum, we just fit line segments where we think there's a continuum, and you can measure absorption bands underneath or the silicon carbide dust emission profile above. The two yellow bars at 6.4 and 9.3 microns, those are measuring the closest thing to continua, which is actually the star plus the dust, because the dust is primarily amorphous carbon and it has no features in the infrared, and so it just makes a pseudo continuum. So using that 6-9 color to break everything up into different classes, all the different spectra plotted in the left-hand side, those are representative of the different classes. And I just want to point out the very bottom spectrum, IRAS 05026, that is actually silicon carbide dust absorption at 11.5 microns. That's a lot of dust. Next slide. So again, taking this information and mapping this back into color space lets us identify the 3 different stages in the evolution of the carbon stars. So stage 1, which is in purple and blue, those are the semi-regular variables. So those are the guys that basically are not making that much dust. And then all the other colors out to brown, those are the Myras. And you could see they make a very tight sequence in pretty much any color space, because it's just a question of how much amorphous carbon there is. And so if it gets red in one color, it's going to get red in the other 2. And then finally, you'll notice that there's a break in the density of points at about 3.6 minus 4.5 magnitude of about 1.5 or 1.6 or so. And everything on the other side of that are the extremely red objects. That's what these were called by Rob Grundle back in 2008. And those guys, they followed up on these, and those are all carbon rich. So this is a spectroscopic plot. I want to point out that photometrically, the discontinuity in the number density between 2 and 3 would be even be much larger, because we only observed a small fraction of the Myras, but we observed most of the EROs. Slide 8. So one of the issues that we've always been interested in was exploring metallicity. And so we wanted to compare the SMC and the LMC to the galaxy. And to do that, we had 42 spectra from the short wavelength spectrometer and ISO. But the sample doesn't quite match up with the Magellanic samples. And we needed more semi-regular variables, and we needed more long period variables so that we could do a better job of comparing like to like. So we proposed to basically fill out the galactic sample with the forecast grisms on SOFIA, and we got 33 more spectra. So not quite doubling the sample, but close. And you can see here, bottom left, so a comparison between the SWS and SOFIA spectra of similar objects. And you'll see there's a gap because of the grism coverage between 8 and 8.5 microns. And then there's another gap where we've just basically ignored the data around the telluric ozone feature, because it's really difficult to calibrate through that. But you can see, other than that, though, you can see the difference between a carbon sulfide molecular band and then acetylene absorption bands. Slide 9. So first, let's look at the difference between stages 1 and 2, the semi-regulars and the Myra variables. So on the left, we've got the silicon carbide dust strength normalized to the total continuum underneath, which is, remember, star plus amorphous carbon, and plotted as a function of the 6-9 color, which is how much amorphous carbon we're seeing. And you'll notice that the separation between SRBs and Myras is really quite striking and quite clean in this diagram. The semi-regular variables are not producing a lot of dust, but the dust that they are making is silicon carbide. So you add a little bit of dust, it's all you add a very strong silicon carbide feature very quickly. And then once you're dealing with stars that are pulsating strongly in the fundamental mode, more dust is added, but it's amorphous carbon. And so the silicon carbide feature slowly gets swamped by the amorphous carbon dust. And then on the right-hand side is a close-up of the color space I showed before, but now for the LMC. And because there's so many data points to keep track of, we plotted this as a Hess diagram. And I just want to emphasize that if it's a semi-regular, it's pulsating weakly. It doesn't matter which mode it's in. The overtone and the fundamental mode pulsators occupy the very same real estate on this color plot. There's no distinction between them. And then if it's a Myra, then you can see that those are the stars that are clearly dusty. So one of the questions that we have tried to answer, but we have not yet demonstrated that this is correct, is what causes the spread in the 5-8 color in the semi-regulars. Slide 10. Basically, we think it's the carbon-3, which has a very strong absorption feature at about 5 microns. CO could also contribute, I should add. But what that would do is if you have very strong molecular absorption at 5 microns, that would basically remove a lot of flux that you would normally see in the 5.8 micron filter, and that would make the 5.8 -8 color pretty red. And so you can see a comparison of different stars here, and T Lyra has a very strong feature, so it would be very red, kind of high up on that diagram. Next slide, please. There are more molecules to be seen here, and because we're looking at semi-regulars, there's not a lot of dust, so we can see right down to the photosphere. And with the galactic sample doubled in size, we were able to, in the paper that Kathleen led, we were able to distinguish between carbon sulfide and acetylene. And what's interesting is if you plot the equivalent width versus the apparent centroid of the molecular band as observed by Sophia, because we miss a chunk of it, so it's not the true centroid of the band, but you can see that there's a very clear dichotomy in the spectra. And basically what this is telling us is that almost all of the Myras have an acetylene band, and the semi-regulars are split pretty evenly between carbon sulfide and acetylene. We don't know why, and we haven't yet figured out what distinguishes the two groups of semi-regulars. Slide 12. So let's go and look at the difference between stages 2 and 3, between Myras and the EROs. What I want to point out on the left-hand side is, well, first of all, I should back up. The WISE mission has contributed a lot to this figure, because in its new guise as NeoWise, and then as NeoWise R for reactivated, which apparently is pronounced Neo-Wiser, we get another photometric epoch at 3.4 and 4.6 microns every 6 months in the LMC and SMC. And so, and they just keep coming. And so 4.6 and 4.5 microns are pretty close together, and the color transformations are pretty easy. So on the left-hand side, the standard deviation in 4.5 also includes all the WISE epochs that we could get up to the point this was published. I think this wasn't updated, but it pretty much looks very similar now. The point is that the variability of the carbon stars as you go up the Myra sequence increases as they get redder, but you can see that once you get to a 5.8 -8 color of about 1.5, that's the maximum variability. And from that point on, the variability diminishes as the stars get redder. Peter Wood has suggested that we looked at this, and we did, and this confirmed what he thought was happening, which is that these stars have actually ejected their atmospheres. They have nothing left to pulsate. And so that's a sign that the EROs have actually departed the AGB. And another sign appears on the plot on the right-hand side. Can you go to the next slide? Because I just circled the 3 problematic sources. The reddest EROs in 5.8 -8 color also show an excess at 3.6 microns, which gives them a bluer 3.6 -4.5 color. And just as Roberta had mentioned before, for VY Canis Majoris, which by the way, I've always pronounced Vicky, if you have holes in the dust shell, then you can see light escaping the shell, light from the star, and scattering into your line of sight. And that's what we think is happening. So we think these shells are losing their spherical integrity. Slide 14.
1.5 minute warning.
That is perfect, because I have like 1.5 slides left. So the next question is, well, what's next for these guys? And this is very speculative, but this is what some of these objects, which we know are carbon rich and have left the AGB, look like. So these are post-AGB objects. This is Westbrook, the Westbrook Nebula on the left and the Cygnus Egg on the right. And the point is that they have a very nice bipolar morphology in optical light, because that's the scattering. All right, and then one more slide. Yes, that would be the summary slide. So just to review, the 3 stages in the lives of carbon-rich AGB stars. First, we see them as semi-regular variables. The pulsations are weak. They can be overtoned or fundamental. Neither mode dominates. The dust production is weak. What is there is mostly silicon carbide, and they generally show pretty strong and interesting molecular absorption because we can see the photosphere. The second stage is the Myra variable. So now we have the fundamental mode dominating, gets quite strong, and associated with that is very strong dust production of amorphous carbon dust. And then the third stage are the extremely red objects, which are giving us signs that they're leaving the AGB, which is why I asked the question earlier about what's the zero age for a planetary nebula, because this ought to be it. Well, if we're right. Anyway, that was my last slide, and that's all I got.
Thanks, Greg. That was perfectly timed. So we have a couple minutes for questions. Patricia, go ahead.
Great talk, Greg. Lovely to hear your explanation of the EROs. I just want to question that the dust shell was ever symmetric.
That's.
I think there's lots of evidence that it isn't at really any stage, and that the dust, particularly from carbon stars, comes off in puffs in random direction. A bit like we're hearing for the supergiants from Roberta just a while ago.
Sure. The only question I would ask then is that why don't we see any light from the central star at an earlier stage?
Sorry, why don't we see light from which one? Which
From the for stage 2, we don't see the blue excess, and my question is, if we that something has changed between stage 2 and 3 to allow us to see that blue excess. So sure, maybe they weren't spherically symmetric in the first place, but I guess was it reasonable to presume that they're less spherically symmetric now?
I don't know. Interesting.
Great, thanks, Patricia. I can't see if there's anything in the chat. So if someone sees something in the chat, please pipe up.
Nothing in day 4. So I think we're good. We could try to get us back on schedule, regain 3 minutes.
All right, thanks, Greg.
Yeah, thank you. Thanks for doing my
slides. We're gonna keep going with carbon stars. So now we have Mark Siebert, who's going to be talking about investigating clumpy cyanide chemistry in the envelope of IRC 10216. So Mark, if you'd like to...
I don't think I'm a co-host yet.
Oh, let me go ahead and make you co-host. Okay, there you go.
All right, let me grab my slides. All right, how does that look? Can everyone see them?
Looks great.
Awesome. Well, thank you, Steve, for the introduction. And thank you to all the organizers for putting this all together and allowing me to share some of my recent work on IRC 10216. My name is Mark Siebert. I'm a second-year graduate student at the University of Virginia. And I started working on chemistry in AGB envelopes when I first started graduate school a couple of years ago. And this is the first time I've had the opportunity to meet the community, so I'm very thankful for that. And without further ado, the subject of this talk is the very famous carbon star IRC 10216, which I'm sure many people have heard of, at least because it's actually come up a few times in previous talks this week. Now, IRC 10216 is one of the most famous carbon-rich AGB stars. It has an extremely high C/O ratio of about 1.4. It's very red, and it's losing mass at an estimated about 2 × 10⁻⁵ solar masses per year. And what really makes it unique and stand out above the crowd is its very close distance of about 130 parsecs. And for something that is losing mass at such a high rate and that is so close, that makes it an extremely bright molecular line object. And actually, this year is the 50th anniversary of when CO was first detected in IRC 10216. It was in Solomon et al. 1971, and I'm pretty sure it was the second source where CO was ever detected. So this is really one of the greats when it comes to astrochemical environments. And to date, since it's been hit with so many single dish surveys since that detection 50 years ago, out of some 200 molecules, I think this number is even a little bit out of date since when I made these slides, almost a quarter of all the known interstellar molecules were first discovered in IRC 10216. So it's really famous, and this all just goes to show that IRC, it really represents the basis of our knowledge on how chemistry proceeds in carbon-rich AGB outflows. And the way, the model of how, the popular model of how that chemistry proceeds is that in the inner regions near the stellar photosphere, you have a combination of equilibrium and some shock-induced chemistry forming parent molecules like CO, HCN, SIS, usually very small molecules, and also acetylene. And once those are released into the ISM by being coupled to the dust grains that escape via radiation pressure, once they get far enough away from the star that the UV flux is high enough, they start undergoing photochemistry, which is dominated by kinetic reactions and UV photons breaking apart these parent molecules so they can form these exotic products. And these would be things like the cyanopolylene molecules, these long linear carbon chains, in addition to their non-nitrogen bearing polyene counterparts. And then also the metal cyanides that were found in this source at a very early date. And the way that we always thought about how this worked would be that these photochemistry products that happened later in the envelope, models of single dish lines and photochemical models predicted that these would peak in abundance starting at about 10 arc seconds. And depending on which molecule you're looking at, it could shift outward from that. But that's generally what we thought, and the single dish observations tended to match that by fitting line profiles based on the beam size of whatever telescope you're using. So when ALMA came around and we were able to actually image some of these molecules, we started to see some really interesting results with these photochemistry products. And there's one work from Marcelino Agúndez in 2017 that has these beautiful maps of the cyanopolylene molecules as well as the polyene molecules. I only have the nitrogen species here. But these results tended to agree with what we thought about this kind of chemistry, that CN, which is formed through the photo dissociation of HCN, which is a parent molecule, starts to appear around 10 arc seconds. And once you have CN appearing, then CN can undergo reactions with other species in the wind, other atoms in the wind, and you can get these very radical products like the cyanopolyenes. In this case, it would be a reaction of CN with acetylene to form HC3N, and then you can have subsequent reactions to form things as long as HC5N and HC9N has actually been detected in IRC as well. So this all matched very well with the understanding of chemistry in IRC. But other molecules that also bear this carbon triple bond nitrogen piece showed a very different result, like with sodium cyanide and with methyl cyanide, which were shown to have very, very compact emission regions. So sodium cyanide, and this was very interesting given that magnesium isocyanide is present at those sort of 15 arc second, those outer regions. Sodium cyanide was instead constrained to a size of about 5 arc seconds, and just on the 1 to 5 arc second scale. And similarly, methyl cyanide was observed to have a ring of emission at about 2 arc seconds, which is very hard to reproduce with the photochemical models of this source, and really sort of presented this puzzle. And so I read these papers, and I really wanted to tackle this problem from an observational perspective. And to do that, a great way to do that is just to image more molecules with this carbon-nitrogen bond, and also revisit these molecules that have been studied and try to image them at different transitions, because we know that depending on what rotational transition you're mapping, the size of emission you're going to be tracing different parts of the wind depending on what you're studying. So I really wanted to fill out this picture with more interferometric work. And to do that, we looked at the ALMA archive. And specifically, we found this project that was done at band 7. Did a spectral scan going from about 330 gigahertz to 345 gigahertz. And it has a wonderful spectral sensitivity and an angular resolution of about 0.8 arc seconds, which is really important for resolving out that emission at those really close scales. And we detected emission from over 20 molecules. It's a very crowded region in the millimeter at these frequencies. But among those 20, we have high energy transitions of methyl cyanide, sodium cyanide, and most importantly, possibly, is HC3N. So we took these data and I cleaned images for everything to see what was going on, and having one set of data to compare all these molecules together is really helpful for being able to see, compare where they're forming and where they're emitting, and how this chemistry might be related. So now I'm going to move on to my preliminary results for this project. These maps will all come out in a paper probably later this year. And we're going to start with HC3N, cyanoacetylene. So in Agundez et al., they looked at HC3N at band 3. So this is the J equals 12 to 11 transition, which has an upper state energy of about 34 Kelvin. And this is sort of what we expected. It's at a radius of about 10 arc seconds. But if we look at this molecule at band 7, we're naturally going to jump up to a much higher energy state for HC3N. And what we saw was actually really interesting, is that the emission of HC3N at band 7 is tracing completely different gas than it was at band 3. So this map that I made is completely contained within the rings that were found in this paper. And that is really exciting, and it really just has to do with this fact that we're tracing these higher angular momentum states for this molecule. The temperatures in this region are on the hundreds of Kelvin scale, sort of. And if we look closer at this emission, we see it has a ton of structure. It's really interesting. It has a central ring at about 1 arc second. And then surrounding that central ring, it has various arcs and knots sort of coming out of it. And especially one knot to the southwest, which we've dubbed the Southwest Clump, appears very bright, about 3 times as bright as the rest of the ring. And then, so these arcs go out to a radius of about 5 arc seconds, and then they steeply drop off after that. And we thought about whether or not this was because the molecule actually wasn't present at these radii, and we would, with the field of view of ALMA at band 7, we would be able to just pick up those rings from band 3 on the outside of our primary beam. But when we looked into it, we found that the reason that we're not seeing HC3N at these higher distances is not because it's not there, but it's because of excitation effects. So the critical density of this HC3N line is much, much higher, I think 3 orders of magnitude higher than the ones at band 3. So it's going to be subthermally excited in those less dense outer regions, and we're not going to pick up any emission from this 323 Kelvin line. So to compare these sort of asymmetries that we see with the structure of the envelope itself, we also imaged 13CO, the J equals 3 to 2 transition. And comparing these two is very interesting because we see that the really only departures between the two are that HC3N is lacking the central peak, meaning it is not present at these innermost radii where a parent species like CO is produced. But outside of that, it follows a very similar structure. All the knots and arcs are about the same. So whatever is producing HC3N at these inner radii it's happening somewhat isotropically. And then it obviously does not trace those outer regions where we see these other arcs and knots. So that was very interesting to see. And we can also compare it with some of the molecules that were studied previously, like methyl cyanide. So with methyl cyanide back in 2015, when it was first mapped, this was done at band 6. So it's not quite as large of a jump in angular momentum state. So we're jumping from an upper state energy of about 156 Kelvin to an energy of about 215 Kelvin. And we were happy to see that we fairly accurately reproduced the map from this work as well. But what is very useful about these band 7 data is that we actually detect the K components, the K components of this 18 to 17 transition up to K equals 9. And that allows us to actually get at those higher energy states of CH3CN. And we see that as we move upward in the K quantum number, the emission becomes more and more compact until K equals 9, where it's very, very constrained. And we're still not entirely sure if it actually overlaps with the star itself. That requires a little bit more analysis. But an important thing to note is that the southwest region that I pointed out with HC3N also appears bright in all of these as well.
Hey, Mark, 2 minutes?
Yep, okay, thank you. And another thing that we can do with methyl cyanide is that because this is a symmetric top molecule and we have these different K components, something that's really nice about that is that quantum mechanical selection rules prevent you from radiatively transitioning between different K components, which means that the temperature that dictates the population among the K ladders is completely governed by collisions. So if we actually extract a spectrum at some of these clumps, we can actually measure the kinetic temperature in those gas clumps. So this is a rotation diagram of the region extracted spectrum on the southwest region, and then we also defined one on the northwest region as well. And we see that it's very well fit by a single temperature, and that temperature in this case is around 200 Kelvin for both clumps, which is definitely in agreement with the standard temperature profiles in IRC. Lastly, we can compare this with maps of sodium cyanide. We only have one unblended transition of this molecule in band 7. And the results from this are not that much different from Guillermo Quintana-Lacassi's work in 2017, which is that it peaks at a distance of about 1 arc second and then quickly falls off. And we just barely are able to pick up emission in that southwest region once again. We also looked for other metal cyanides like magnesium isocyanide, which is not detected at these radii, and we confirmed that further as well. So what does all of this mean? Well, it means that these band 7 data that we use were really useful to help build out the picture of these cyanide molecules in IRC. And you can always learn new things about these molecules by studying these transitions at different excitation conditions. And this is just further evidence that the CN photochemistry is occurring in these warm inner clumps of IRC. And in the case of HC3N, they match the wind structure of like 13CO, but in the case of CH3CN, it's a little bit more anisotropic. There are clumps that appear much brighter, and we're not sure if that's because of the different formation routes to this molecule or whether that could just be excitation effects. But thank you for listening to my talk, and I'm happy to take any questions.
Great, thanks, Mark. Any questions? Yep, Marie, go ahead.
Hi, Mark. Thanks for the very interesting talk. I was wondering whether you also noticed the radial sequences that have been talked about in the literature of HC3 and HC5, and I'm not sure whether you have those data available, but there's the co-spatiality and then the radial sequence of the cyanopolyeins and the hydrocarbon radicals.
Are you referring to like how they kind of go out?
Yeah.
They're a little bit bigger. Yeah. Yeah. So we also looked for larger carbon chain species like HC5N or C4H, but those are also all not present at these inner regions. So my guess is probably that those photochemical reactions are not occurring fast enough as HC3N, which is expected to be sort of the first of those chain species to occur.
Okay. Thanks.
Time for another question. We got another hand from Yuan. Go ahead.
Hi, that was really interesting talk. I have a pretty naive question. So what causes the clumpiness in these objects?
Yeah, that's a great work. That's a great question, and there's been a lot of great work done on the mass loss history of IRC and really looking at these clumps and modeling what could be creating them. And a current theory that is very popular is that IRC has a binary companion that is perturbing the steady wind component and is causing these sort of loops and arcs to form. So that's a very likely explanation. Another one would be some sort of anisotropic mass loss that is going in different directions if you at different points in time, kind of.
Thank you.
All right, any more questions?
I can't figure out how to raise my hand. It's like it's not on my menu here. I was just going to comment that Patricia kind of answered that question when she was asking me a question in the last talk, which is that the mass loss and the dust production might just be, just poofing in random directions, so inherently clumpy.
All right, thanks, Greg. So unless there's any other questions, I think we can stop for our break. We'll be returning at 10 past the hour for our discussion section, which is going to be on mass loss across the HR diagram. It won't be recorded, so no pressure. But we're going to head over to GatherTown, and I just wanted to thank again all of the speakers for their fantastic talks. So again, we'll start back at 10 past and enjoy GatherTown. Anything else to say, Marie or Thaisa?
Yep, we're all good.
All right. Thanks, everybody.